By Rajdeep Sensarma from TIFR. He'll talk to us about spectral functions in bilayer graphene.
Okay, I'd like to thank the speakers here. Sorry, the organizers for inviting me. I don't want to thank myself. Sorry. Yeah. Okay, so I changed my title a little bit, and you will see why. Because I was here when Jim was giving his very nice talk on exciton condensation in bilayer quantum Hall systems. And we had done some thing about exciton condensation in double layer graphenes. So I wanted to add that, and so I changed the title a little bit. So I'll talk about electron-electron interactions in bilayer and double layer graphene. And although I've joined Tata Institute of Fundamental Research recently, this work has mainly been done at Condensed Matter Theory Center in University of Maryland. And these are my collaborators, Shankar, who was my mentor at the postdoc level, Yuhyun Wang, who was at Maryland, and he's now in Korea now, and David Abergel, who was again a postdoc at Maryland. So here's the outline of the talk. I'll give a very brief intro about what kind of systems we are considering, what is graphene, bilayer graphene, and double layer graphene. It can be confusing, and there are too many layers here, so I'll just tell you exactly what I mean when I say bilayer and double layer graphene. We'll talk a little bit about dynamic screening and plasmons in bilayer graphene. And this is a little detour. I will try to cover it very quickly about Plasmon-phonon couplings in monolayer and bilayer graphene. And then I'll come to single particle spectral function in bilayer graphene. And the idea is you need this dynamic screening functions to calculate the single particle spectral function. And finally, as I promised, I'll talk a little bit about exciton condensation in double layer graphene. So graphene, as you know, Andre Geim and Novoselav, they got the Nobel Prize in 2010. It's essentially a single sheet of carbon atoms arranged in a honeycomb lattice. And for the purpose of this talk, what we will look at is that it gives us A and B sublattice, so it provides the pseudo-spin degrees of freedom. And there is a tight binding model which says I just have tunneling from A to B sublattice, some nearest neighbor tunneling problem. And if you do that tight binding band structure, you find that you basically have two bands, and they actually touch each other at 6 points in the Brillouin zone. However, three of the points are basically two of the points are inequivalent. There are pairs of 3 points which are connected by lattice vectors. And so we get two valleys around points k and k prime. Now if you expand around k and k prime, you'll see that the dispersion is linear, and we get a Dirac Hamiltonian in 2D. And there are very nice review articles by Shankar and by Kotov et al. And if you want to look at those, you can just, if you want to know more about this. So here is what graphene looks like. You basically have 6 Dirac cones, and essentially in the end, we'll think of them as only 2 Dirac cones. So we have a linear dispersion in the 2 bands, plus and minus 1. And the graphene Fermi velocity is 10 to the power 6 meters per second, and in this sense, it plays the role of speed of light in these systems. And it has gapless chiral bands. So if you look at the band wave function, you will see that the band wave function has a e to the power minus I theta, which denotes the chirality of the bands. And in these systems, density can be tuned by applying a gate voltage, basically. Let's come to bilayer graphene, because we'll be talking a lot about bilayer graphene. So it's basically 2 sheets of graphene stacked on top of each other. But it's on Barnell or AB stacking, so A atoms in one layer basically sit on top of B atoms in the other layer. And these two layers are very close by, so there's a very strong tunnel coupling between these two layers. I mean, you can almost think of it as some effective two-band system. So if you do the full calculation, then you come up with the fact that you actually have a 4-band model, but 2 of these bands are gapped out on a scale of 0.3 eV. So for the purpose of low energy physics, we will neglect them, and we will work with a 2-band model. So the Hamiltonian is given here. You get 2 parabolic bands which are touching each other. Now this is important, because you might say, what is the big deal with 2 bands? I mean, we get this in semiconductors. So the point here is these bands touching each other, there's no band gap as such. So it's a parabolic dispersion with no band gap. And that's basically what it will look as in the non-interacting limit. So here is the dispersion. It is sk squared over 2m plus minus 1. You get 2 parabolic bands. Now forget about the hyperbolic dispersion. I mean, if you go to large enough momenta, the dispersion changes a little bit. This also has chiral bands, but look here, the angle is e to the power 2y theta, which means if I wind around, the winding is twice. Again, the density can be tuned in these systems by applying an electric field. And we can, in principle, gap these 2 bands out by applying an electric field in between the layers, not in the same direction. But that will not be important for the talk we are going to look at. And finally, double layer graphene is a system like this. Again, you have 2 sheets of graphene. So what's the difference between double layer graphene and bilayer graphene? Is that they are separated by a much larger distance. This is actually, you grow it, you put a layer of graphene, then the layer of dielectric, and then the layer of graphene together.
So you're going to assume that it's still Barnell stacking?
I'm going to assume there's still Barnell stacking, but in some sense that will not be important because I'm not going to consider tunneling between these. Yeah. So in some sense it's irrelevant because I'm not going to tunnel from one layer to another. So tunneling between these layers is negligible, whereas bilayer graphene is very strongly tunnel coupled. And for our purpose, we'll set it to 0. However, the electrons in one layer can interact with electrons in the other layer by Coulomb interaction. So the 2 layers are coupled only by Coulomb interaction. And in the case that we will consider, it will become clear why we will consider this. One layer will be electron doped, let's say the upper layer. And one layer will be hole doped, let's say the lower layer. So, oh, this is both electron doped? Sorry, no, the lower layer, other layer is hole doped. Sorry for the time. One more thing about, since we are going to talk about electron-electron interactions, effect of electron-electron interactions. So in 2D, bare Coulomb potential has a 1 over q, but it's characterized by a dimensionless parameter Rs. Now in graphene, since you have linear density of states, Rs is E square over kappa Vf. Now Vf is basically the graphene Fermi velocity and it's given to you. So the only thing you can change Rs by is by changing kappa. So it can take a few discrete values, and Rs is of the order of 1 for most standard substrates. So you don't have much chance of tuning the dimensionless interaction strength. Compared to that, in bilayer graphene, you have a parabolic band dispersion, and in the expression for Rs, there's a 1 over Kf sitting here. Which means if I can change and Rs basically goes as density to the power minus half, if I can change the carrier density, I can go from weakly interacting to strongly interacting systems by tuning the density of carriers. And to give you a rough idea of the numbers, if you have 10 to the power 12 per centimeter square carrier density in vacuum, Rs is of the order of 10. Yeah, kappa is 1. I'm just trying to give a number because if you put some kappa, then it will change. This is just, yeah.
I sort of miss the obviousness of that when there's no tunneling but there's electron-electron interaction, that the stacking doesn't matter. Right? Maybe it's true and maybe everyone knows it, but it doesn't seem obvious to me. I mean, even the angle between the two of them would make a difference.
No, it's.
Is that? I don't know. Did anyone say that?
No.
If the distance is very
Yeah. But if the distance is large, so you
If the
can.
distance is large, then that's a different problem.
That's the problem I'm going to look
Say
at.
the distance is large, then okay, then.
No, that's what I said. We are going to look at things which are not tunnel coupled and they are at large distances. So the one other way of saying is if you want to look at the Coulomb interaction, the way the tunneling would matter is you have a D, and actually if it's moved a little bit, you have a D plus delta X. So the question is whether this delta X stuff matters in the Coulomb interaction. And if D is much larger than typical lattice spacings, then it won't.
I see. So there's one scale which sets the tunneling rate, which also sets this lateral dimension.
Yeah. So that's basically.
Which happens to be the same physical dimension.
Yeah.
Thank you. That's good.
Okay. And finally, for double layer graphene, we would need to look at the Coulomb interaction between the two layers. And this is given by the standard Coulomb interaction 1 over q, but there is an exponential minus qd, where d is the basically the distance between the two layers.
And this d is much larger than lattice spacing.
Much larger than lattice
Take care
spacing.
of the question Charlie was asking.
That's where, it's essentially that. So let's first look at dynamic screening and plasmons in bilayer graphene. This is work done with Yuhan Wang and Shankar Sharma. And in 2D, what happens is you get a bare Coulomb interaction, but then electrons effectively start to screen this Coulomb interaction. And this screening can be expressed in terms of a dielectric function, which is a function of both wave vector and frequency. For example, in 2D electron gas, you have a Linhart function, very celebrated Linhart function. And our claim is that actually for bilayer graphene, we have an analytic expression for this, which is equivalent to saying we have a Linhart type expression for the bilayer graphene epsilon. Now in static limit, this controls transport properties and so on, but for dynamic screening, this actually governs the collective plasmon modes, and this is crucial in getting single particle properties, spectral properties, which what we are after. So it's a two-band system, and if you take the random phase approximation, then you get the VQ, the epsilon q omega is 1 minus VQ times some polarization functions. And the polarization functions, the G is a degeneracy factor of 4, and polarization functions are given by standard Fermi functions here, and then there is a dispersion coming in here. And this FSS prime k plus q is a wave function overlap factor, which comes because I have chiral wave functions. And this is the form of FSS prime, and theta is the angle between the two momentum. Now, if we assume the chemical potential is in the conduction band, we can think of intraband polarization as following, where intraband polarization is where the band index is same. So essentially what happens is you are making electron hole pairs, but in the same band. And interband polarization is when you are basically trying to promote this guy up there, so you're making a hole in the valence band. So we have a complicated analytic formula. I don't want to write it down, and it will take me more than one slide. But here is some pictures. I have the imaginary part of the intraband polarization, and there are some interesting additional cusps. I mean, this is very 2D-like result. There are some additional extra cusps in this when you go to higher wave vectors. And again, if you look at interband polarization, so the one thing to notice is that you actually have density of states going up to very high energies, and that's because you have a field Fermi C, which is in the lower band, and that's basically what is giving you this large spectral weight there. So if you can look at the plasmons, so the plasmon dispersion is given as, it goes as root 2 RS, and then there's a root over Q. This is the classical 2D plasmon. And then there's a fast order, the fast quantum correction is negative, and the idea is that you have two bands, and corresponding to that you have two particle hole continuum, and when this goes up close to this, there's a band bending effect. So the plasmon basically has a negative correction here. So if you want to compare just the plasmon dispersion, you would see that it goes as omega naught q to the power half. That's just 2D classical result. And then there is a correction. So if I consider bilayer graphene, it goes as n to the power half, which is a standard 2D result. That just comes from density of states. And single layer graphene, it goes as n to the power 1/4, which basically reflects the fact that you have a linear density of states. And again, alpha, which will be something like the Thomas Fermi wave vector kind of thing. Here is independent of density. Here it goes as n to the power half, and again in 2D it's independent of density. Now, one thing which is interesting is both in bilayer and single layer graphene, alpha is greater than 0, so there's band bending effects because you have two bands, two particle hole continuum. Whereas in 2D it's actually less than 0, so your plasmon actually goes up from quantum corrections. And here are some graphs showing how the bilayer and the single layer compare for given values of kappa and so on as a function of Q. Sorry? No. By the time you go there, you would have higher correction. I mean, you see the full dispersion here. It never goes to 0. It never becomes large. But you can ask what is the next order correction, and the answer is the correction is negative. Whereas in the other case, in standard 2D, the plasmon correction is positive.
So in double layer ordinary 2D gases,
yeah.
there's a linearly dispersed plasma.
Right.
You don't have that in
No, because it's strongly tunnel coupled. I mean, so that linear mode exists when you have very.
It presumably will come up in the double layer.
Yeah, although double layer we're not looking. I think Shankar and Yuan had a paper where they calculated it for the double layer graphene, and it comes out, and you can. So forget about the hyperbolic dispersion, and this is the optical spectral weight. This is actually the experimentally measurable quantity because this can be measured by inelastic light scattering or inelastic electron energy loss type experiment. And the three pictures correspond to the case when there's actually a plasmon pole, and there's some continuum of excitations. And this lies in the gap between interband and intraband continuum. Here the plasmon has gone into the continuum, and so it's broadened. And here you actually don't have a plasmon pole, but you have a residual signature. And you can look at if you are close to the plasmon pole, you can have a spectral weight of the plasmon and a broadening of the plasmon. And so here is what the spectral weight is plotted. And this feature where you see a cusp-like feature basically is where it is entering the continuum, the interband continuum. And once it enters the interband continuum, you basically have a broadening starting. I'll very quickly go through Plasmon-phonon coupling. So there were these experimental papers which saw these two sort of bands of plasmons when experiments were done. And there was some sort of a quasi-linear behavior in this upper channel. And we said that it could come from electron-phonon interactions. And this is not coupling to phonons of the graphene, it's coupling to phonons of the substrate. So you have basically polar substrates, and so you can have Froelich type coupling. And that basically, I think instead of looking at this details, this is one way of understanding it. You had your original interaction, this is your Coulomb interaction, but now the electrons can interact with the phonon, so that can give you an effective vortex, so which can renormalize your effective polarization and epsilon and so on. So you can do this whole theory, and you can calculate the dielectric function, and from that you can get the optical spectral weight. And here is the idea that in a monolayer graphene, lo and behold, you do see two features. And here is the spectral weight plotted. So you get a low energy mode which goes as square root Q, and a gap mode with a linear dispersion. And there's a strong plasmon-phonon coupling at all densities, basically. And there's a large spectral weight in the gap mode, as you can see from these two calculations. Now, if you go to bilayer graphene, it changes, and you get these two modes. But there's a difference in behavior. At high density, you have very strong plasmon-phonon coupling. And the idea is that this actually lies below the interband continuum. And so you get a linearly increasing gap mode. And at low densities, you have very weak plasmon-phonon coupling. And the idea is this has already gone into the interband continuum. So there is not. And the plasmon has also, basically, the free plasmon has already gone into the continuum. And so there's not much coupling between these two. So there's a very concrete prediction that if you do look at these things in bilayer graphene as opposed to monolayer graphene, you would see very different behavior as a function of density. Let me go to the part which I was put in my initial title. It's a single particle spectral function in bilayer graphene. And this was again work done with Yuhen and Shankar. And so the spectral function is obviously the imaginary part of the Green's one particle Green's function. And the effects of Coulomb interaction can be captured by putting in a self-energy term. So this is your free Green's function, and then you modify it by a self-energy, which has an imaginary and a real part. So if you go to bilayer graphene, what happens is you get, so simplest thing you can do is a Hartree-Fock calculation. You can say, okay, what's the big deal? I can do a Hartree-Fock. Now, Hartree-Fock actually diverges because the field valence band, which extends up to very large K. Of course, in reality, a bandwidth will come in, and that would give you a cutoff. But so what happens is these cutoffs are needed to regularize the results. So for example, if you look at quasi-particle mass, it would depend very strongly on your cutoff. So that's not a very nice thing, at least for theoretical physicists to think about. So so we are interested in low energy Pock properties for now. So let's look at the G+, and we are assuming that the Fermi level is in the plus band, conduction band. So you can do an RPA with dynamic screening. So basically what that amounts to is that you do an exchange calculation, but actually you have the full frequency and omega dependent screened interaction here. And these are technical terms, things for those who are used to doing this sort of calculation. You can break the self-energy up into two parts and so on. But what is important is you will see everywhere this 1 over epsilon q omega coming in. And this is where having an analytic expression gives us a much more advantage. Like we can do these calculations much faster and without actually having to calculate epsilon numerically. So here is the self-energy. So at k equal to kf, this is sort of featureless. There is nothing much going on here. Away from k equal to kf, you suddenly start to see logarithmic singularities in the imaginary part. And these logarithmic singularities are basically coming because you are scattering of plasmons, and this is some plasmon edge effect. So, and it happens both when your k is greater than kf and k is less than kf. And we will see that these plasmon scattering effects have closely related things in spectral functions. They will show up in spectral functions. Here is a corresponding spectral function. Rs equal to 3 is, I've just chosen to show one here. We have for various other stuff. So you of course get, let's first look at k equal to kf. You have a delta function at the Fermi level. And then there is some broad distribution of spectral weight because your interaction has shifted spectral weights to larger energies. You go away from k equal to kf. This is your Landau quasi-particle peak. It's a little broadened. But then you see the second peak structure. The second peak structure is basically what is known in the literature as Plasmaron. It's basically a quasi-particle which is dressed by the plasmons. And you see that both, if you go k below kf and k above kf, in both cases you see the plasmaron. Of course, in one case it's below the quasi-particle energy, and in one case it's above the quasi-particle energy. So basically, the Botswick et al. In 2010, basically they looked at this for monolayer graphene, and they found the plasmarons. And Wang and Sharma had done the calculation and have found the plasmarons for monolayer graphene. Unfortunately, for bilayer graphene, there's no published data yet, and so it's hard to compare. Let's focus on the Landau quasi-particle, though. Landau, close to the Fermi surface, it's a pole. It's basically, so if you look at ak omega, it's a delta function. And the weight of the delta function is what is known as the quasi-particle residue. It can be calculated in terms of the energy derivatives of the self-energy. And here is basically the plot of z as a function of Ra is going up to 10. And you see, even at 10, it has not even gone below 0.5. So in some sense, bilayer graphene, even at large RAs or small densities remains a relatively weakly interacting system. And you can also calculate the effective mass, which is how the dispersion, slope of the dispersion. And for technical reasons, there are two different approximations one can do. I will not go into the details. But again, you see that the mass, you look at the scales, m star over m of 1 is basically free Fermi gas, and it's going up to maybe 0.95. And then it's slowly creeping up. So basically what is happening is that even at RS equal to 10, this remains a very weakly interacting system. I mean, if you compare with 2 DEGs, the answer would be around RS equal to 3 or 4 or something. It will start shooting up, and that would give you some sort of divergence and weak crystallization. We can also look at the broadening of the quasi-particles, is the imaginary part, and from there we see the very clear omega square log omega type dependence, which is very standard for 2D Fermi liquids. So there's one thing we need to understand, that there's a work by Barlas and Young, Nandkishore and Levitov is basically showing if you go to exactly the Dirac point, there's no doping, then undoped BLZ is a non-Fermi liquid, and they have some RC calculations showing that it's a non-Fermi liquid. Now, we find that doped BLZ is always a Fermi liquid. By always, I mean, we showed data up to RS equal to 10. We have gone even below there, much above there, and nothing changes essentially. Now, 3 things are different. One is that undoped BLZ has a single Fermi point, where doped BLZ actually has a Fermi surface. And it has a quadratic low energy dispersion if you see it at the k equal to 0 point. But otherwise, you have a linear dispersion around Fermi surface. And in undoped BLZ, the interband scatterings are important down to 0 energy. But by the time you put a Fermi energy, it's cut up by 2 EF. So this is also consistent with the fact that within the RG that Barlas and Young and others do, if you put a chemical potential term, it's a relevant term. And it's relevant at 3 levels. So that's basically saying that the moment you put any chemical potential, you're going to flow out of this non-Fermi liquid fixed point. And so it would be hard to see these NFL features because density fluctuations are always there in bilayer graphene. Finally, I would just 5, 10. Oh yeah, I'm right on time. So finally, to give you a picture, this is the full quasi-particle spectral function as a function of k and omega. You see the red lines, and I've calculated it for 2 different values of RS. So you see the red line, this is your dispersing Landau quasi-particle. And as you go towards the Fermi surface, this is broadening almost goes to 0. As you go away from Fermi surface, you see broadening increasing. This is the second band, the lower band, which is always broadened because it's away from the Fermi level. These are the plasmarons, these yellow things you see here. And then these plasmarons around k equal to 0, they occur at an energy which is much lower than, it's about minus 2 EF. And they have a very large, I shouldn't say very large, I should say relatively large weight. It's about 0.3 or 0.4. And you can do it for different things. So this is what you would see if you did an RPS measurement on bilayer graphene. So in summary, we have looked at the effects of electron-electron interactions and single particle excitations. We got analytic formula for dielectric function. We looked at plasmons in BLG. We looked at how Plasmon-phonon coupling affects plasmons. And we also looked at effects of electron-electron interaction on single particle spectral function, where in addition to the Landau quasi-particle, you basically now get an additional peak, which is the plasmaron. And we calculated the Landau Fermi Liquid parameters from this calculation. Now coming back to the last part, which I said I would talk about a little bit, is work done with David Avergel and Shankar again. So this is question of effect of disorder on exciton condensation in double layer graphene. So I told you what a double layer graphene is, so I'll just skip this slide. Let me just skip this slide. So what are excitons in double layer graphene? So if you have a system like this where you have an upper layer, lower layer, upper layer, it's electron doped, so its chemical potential is here. lower layer is hole doped, so the chemical potential is in the valence band. So you can write the Hamiltonian as a Hamiltonian for upper layer, Hamiltonian for lower layer, and some interaction term. So Hamiltonian for lambda is the layer index. So Hamiltonian for layer lambda has some 2-band dispersion, and plus dot dot dot. And dot 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 means I am right now neglecting intra-layer Coulomb interactions and so on. That might give me a little bit of renormalization of Fermi velocities and stuff, but they're usually small. So that's why I would neglect them. And since I'm interested in phenomena around the Fermi surface, I will only consider the upper band in the upper layer, the conduction band in the upper layer, and the valence band in the lower layer. I'll neglect the other 2 bands. Now, then it's actually much easier to say that, okay, I will keep whatever C dagger plus is basically upper layer, conduction band, and I will call this some A dagger K. I can always try to call this. In the lower layer, I make a particle hole transformation. So I call the C some B dagger. That's my choice. Just. If you do that, then you can write this part, which I didn't tell you what it is, as an interaction which looks very much like a BCS interaction. So it's an attractive interaction, and this FKK prime basically comes from some wave function factors. V is the Coulomb potential. We'll come back to what the form of V is later on. So what happens is if you have equal doping, you essentially have nested Fermi surfaces in the 2 layers. And then attractive interaction would essentially give you a superfluidity. So it's a superfluidity of electrons and hole pairs. So, and that's basically what's called excitonic condensation. And you can write down an excitonic order parameter and so on. And you can essentially take out your old BCS mean field theory and do the calculation with this complicated potential. And this was not, initially, this was first proposed by Honky Min in Alan MacDonald's group. And I'll come back to these papers as we go along. So here is basically delta K as a function of K. And so you see there's a peak at around Kf, and here I'm basically plotting the peak value of the delta. And this is a calculation done with bare Coulomb interaction. We are assuming there's no screening right now. And this was the original proposal of Honky Min from Alan MacDonald. And then Kharitonov and Efetov and Lazovic and Sekulik, what they showed is, okay, but what if I take the screened Coulomb interaction? Let me take the static screening Coulomb approximation. And they showed that the gap drops. And actually this calculation was done here, somewhere here, where the gap drops enormously. And here you see that, here what happens is if I put the bare Coulomb interaction, as I increase my chemical potential, the gap increases because I have an increasing density of states. And here what happens is I have an increasing density of states, which gives me the rise. But then as I increase my Fermi energy, I increase my screening. So at some point the screening overtakes, and basically large screening basically leads to this. Now there's something that if you include dynamic screening, this would be somewhere in between, and that's... Okay, so it's a equivalent of superfluidity of electron hole pairs. Now if you want to consider disorder effects, and why? Because experimentally people have not seen it as yet. So then Anderson's theorem in the superfluid language says that TC is not affected by some potential scattering. And since spin is equivalent to layer index, there's no spin flip scattering. That means you're basically putting things from one layer to another. So there's no spin flip scattering. So you would think it should be very robust to disorder. But
you think of disorder as the same in the 2 layers? Or?
If it is same, then if more or less the surface is same, then I'm coming to that.
Rajdeep, what you mean is momentum scattering.
Momentum scattering is basically not going to give. Momentum scattering of these things wouldn't give you anything.
Momentum scattering meaning disorder, but what I'm asking whether it's the same.
I'm coming to that, exactly. But electron density in graphene is spatially inhomogeneous. It's very inhomogeneous. And we have a lot of experimental evidence from that, some of it from Amir's group and from others. Amir's group's paper is this one in Nature Physics. This was first, basically, it was pointed out in a very difficult calculation by Rossi and Dasharma. what happens is you form electron hole puddles basically around them. This happens due to the presence of charge impurities in the substrates. In some cases, this can also happen from ripples in graphene layers. Now, the width of the density fluctuations are not small. This is 10 to the power 10 or 10 to the power 11 per centimeter square, and they have an approximately Gaussian distribution of densities. So, one way to take care of density fluctuations in a layer can, of course, be converted into a chemical potential fluctuation. Independent chemical, so we basically look at independent chemical potential fluctuations in the two layers with some Gaussian distribution. The sigma n is the width of the density profile, basically. Coming back to Adi's question, difference in chemical potential, this sort of puddling, will act as a magnetic field. So it's basically looks like a problem of superconductivity in a random Zeeman field. So that's basically the problem that will happen. And we are doing an actual honest to solve calculation with putting in actual random Zeeman field right now. But for a first test, we'll use a local density approximation to average over these disorder configurations. So for that, what we need to know is what happens if I have the density chemical potential difference. How does this excitonic state look like? If I know that, then I can average over probabilities of this getting a certain amount of potential difference and so on and so forth. And here is your answer to that. Here what we have done is we have plotted the peak gap as a function of delta mu for a given average density. And see, it's essentially completely flat up to delta mu of the order of 2 delta 0, where delta 0 is the gap at 0 chemical potential difference, or 0 magnetic field in the language. And then it just drops sharply. I mean, to the extent that we could resolve, there is nothing that we can resolve here. So this is, of course, known as the Clarkston-Chandrasekhar limit in the superconductors. And basically what happens is if you have too much density chemical potential difference, it doesn't pay to condense in this state. Now, you could have gone to some other state, which is an FFLO state with finite momentum pairing. And we see no evidence of an FFLO pairing in this. Finally, let me just leave you with 2 graphs. So here what we have done is, so now that we know what the delta and things are as a function of mu plus and mu minus, or delta mu and average chemical potential, we can look at the average gap. So here is D equal to 1 nanometer, which is unrealistic, I guess, for making these things. D equal to 5 nanometer is probably something that can be achieved. And this is for the unscreened Coulomb interaction. And if you go to the same things with static screening, of course, the average gap goes down. I mean, look, this is 1.5 and this is 15 MeV. Finally, what we looked at here is that, okay, average gap is good for thermodynamic properties. But if you want to look at transport, your basic picture is you have patchy things, and then there is some sort of percolation going on between these patches of condensates and non-condensed stuff. For that, what you can look at is the fraction of area of the sample that supports the condensate. Within local density approximation, you can't do any more. And that is plotted here. So you see this line is full condensate. It's like 1, I mean, up to some small errors that we look at. And this is no condensate again up to some point here. And then you get a partial condensate. Once again, you see that you go to D equal to 1 nanometer. This is basically tracking your gap, essentially. And D equal to 5 nanometer with static screening, you almost don't see anything. Sigma n. Sigma n is the basically width of the density profile that I started with. That gives me a width of my chemical potential distribution. And this is just the average chemical potential, which will be set by some gate voltage, let's say. Okay, so this is basically one more thing is that it's much easier to look at transport. I'll leave with the summary that bulk gaps or bulk thermodynamic properties may not be a very good way to look at this. Once you have disorder, you have much better chance of accessing this through transport, because in transport you still see something at D equal to 5 nanometer with static, which is like the static screening is the worst case scenario, but you still see something. In the gap, you don't see anything at all. And so with that, I will stop.
Question? So, I had a couple of questions. One with regards to the static and dynamic screening in bilayers. You've analyzed the case where there's no perpendicular electric field, so the bilayer is not gapped.
Not gapped,
I was wondering how would that change once you induce a gap, since then you've got this Mexican hat type.
Right. So we have done that calculation. Numerically, the problem is that you do not, once you lose the nice parabolic dispersion, you can't do the integrals exactly. So, but anyway, and so the idea there is that, so now, if you were above this Mexican hat, if your chemical potential is essentially above, then nothing much is going to change. I mean, it's basically going, in fact, it's hyperbolic dispersion. You probably just go back to monolayer graphene. So the interesting question is what happens if you have, so what Amir is asking is that if you put an electric field between the layers, you get a dispersion which looks like this. And the interesting question would be what happens if your chemical potential is somewhere here, because then you have two ring-shaped Fermi surfaces. Ring-shaped, two Fermi surfaces like a ring. And then we actually have some, we don't have dynamic calculation as yet, we have the static calculation exactly. And the idea is, one thing you would expect is something happening at delta kf, for example. And at delta kf, indeed, what happens is that if you look at pi of q as a function of q, at delta kf, there is there's a derivative discontinuity happening there. So if you are somewhere close to there, so your screening is changing very fast in that sense. And there's something interesting. You would also probably expect something at k1 plus k2 in principle, but that doesn't happen anything, and there's a reason for that, but forget about that. So the main answer to your question is you would start getting a peak at q, this is q equal to delta kf. This would be something qualitatively different from what I showed in Bilayer Graphene.
Okay, can I ask another? So one other question I had with regards to the exciton condensate is whether you would gain or lose by looking at double bilayer graphene system versus a double monolayer graphene system.
Yeah, so we basically, I don't have a straight away answer for you, because my guess is that, so a lot of these things depend on, let's say, the density of states. Okay, so in one thing which would be different, I can tell you, in bilayer graphene versus monolayer graphene, is that essentially you would have a density of states which is constant in bilayer graphene. I'm just taking the two model. On the other hand, as you increase your densities, you are going down in RS in some sense. So if your effective thing is going down. So I would expect that as you go to higher and higher densities, in some sense it would become weaker. Whereas at least for bare coulomb in monolayer graphene, it basically keeps on increasing. And RS is constant, so your effective coulomb scale is constant, but your density of states is basically increasing. That density of states is constant, and your effective interaction scale is going down on you. So I would. Yeah, so that has been studied much before anything I did by Shankar and others. So, and there I think.
You have a paper on it, Ali.
Excuse me?
Even you have a paper with me on that. And speak. No, so my quick answer, you have not done that calculation, you have thought about it, this calculation take a long time. My guess is, and this was Alan's original motivation also, that double bilayer would be somewhat worse than double monolayer. At least for unscreened situation, which is what Alan has been talking about, precisely for the reason Rajdeep said, the density of state doesn't keep on going up. See, Alan's idea was you go to very high density, then you get a room temperature version of Jeeves' experiment, because density of state is so high. Of course, you're finding there are subtleties which may.
Yeah.
So my answer will be no.
I mean, even for the bare case in graphene, monolayer graphene, there's some sort of saturation as you go to. I mean, it doesn't keep on increasing just like the density of states.
Rajdeep, this when you have the condensate, particularly at high chemical potential, the only disorder you seem to be considering is the potential screening from the Coulomb potential screening of the and which leads to some form of inhomogeneities and puddle formation and so on and so forth.
Or it could come from ripples. I mean, something that gives me density inhomogeneities.
Yeah. The question is, when you increase the chemical potential so much that your the short range scattering dominates. That is, for example, the edges, the other defects which are of atomic scale.
Right.
What happens to the condensate in those cases? I mean, have you considered the short range scattering, the large K changes?
No, we have not considered the short range scatterings, and so in that case, you cannot do. You'll not be able to do for those things. You cannot do a local density approximation like this. In the model that we are doing now, which is a full-fledged, basically Bogoliubov-Dizen calculation with realistic potentials and, let's say, either charge impurities, and we can make those impurities short range if we want. So that's the calculation that is going on, but we will have to wait a little bit for those answers. And one thing you can, there's also this other work known from superconductivity, that gap. You can have superfluidity just in a superconducting case, even after gap closing. It's called gapless superfluidity and so on. But there might be interesting stuff going on there. But we are doing the calculation, and so short answer is we cannot include those things in the way I have done. And we are doing a full-fledged calculation.
Have you thought at all, the discussion was all about zero-magnetic fields.
Mm-hmm. In finite magnetic and Landau levels and so. I have not thought about it as of yet. Yeah, but that would be something interesting to look at.
Any other questions? If not, let's tea outside. Let's thank